the notes for AP Calculus on the topic of parametric formulas with the graphing calculator. So this one says Sammy programs robot A to move across a flat surface over the time interval 0 to 6, where t, here they give you units for time, it's in terms of seconds. And the position of robot A is given by, notice they put a subscript of A, because we've got another robot here. So this is the x-coordinate position and the y-coordinate position of robot A. And then Chase programs robot B to move across the same flat surface over the same time interval, 0 to 6 seconds. And here's the position function for robot B. Use a subscript of B here for the x and y coordinates. And then all of the functions that they're given here are in terms of feet. So we're also given units for position here. So we're going to look at an applied parametric problem. And notice we're moving in 2 dimensions here because we've got the x and y coordinate on this flat surface. And part A says determine the exact time at which the robots collide. And justify your answer. So, in order for them to collide, the positions of the robots, both the x and the y coordinates, are going to need to be equal. But they could cross the same position at different times and they wouldn't necessarily collide. So the positions are equal at the same time. That's what's required in order for them to collide. At the same time, they're at the same position. So let's start with the x-coordinates. That means x sub b of t would have to equal, actually we'll put a first, x sub a of t, the x-coordinate of robot A, which are given right here, would have to equal x sub b of t, the x-coordinate of robot B right here. Alright, so let's go ahead and see if we can figure out where those two are equal. Notice this is a graphing calculator problem. This one would be kind of tough to solve with exponential and the root in the same equation if you just try to set them equal to each other and solve by hand. So let's look at the 84 first. So to change it to parametric mode on the 84, just hit the mode button. And then normally it's on function mode, regular function mode. And we still will use that, but we're going to switch it to par here, stands for parametric. Hit enter on that. And then you can quit out of here. And then when you hit y equals, notice it looks a little different. So x1t, that is our x coordinate. We'll use robot A and robot B for x2. So x sub A for robot A would be 2. Now when you hit the xt theta n button in parametric mode, it's going to put it as t. And then divided by, and then parentheses, because we've got 2 terms on the denominator, t plus 4, close parentheses. And the y-coordinate would be e, it already puts the open parentheses for you, t minus 4, close parentheses, and then minus 6. And then for x sub 2, that's the square root of t. Y2 is 0.5 or 1/2 t squared minus 3t minus 1. All right, and then when you hit window here, so for the window size, notice your t min and t max were given right here. So, write this on here. So your interval says it only applies from 0 to 6. This is your t minimum, 0, and your t maximum right here is 6 on your window size. And then the steps, t-step, that you can usually leave alone here. This just tells you how often, in this case about 0.13, how often it's going to plot a point for t. Every, in this case, 0.13 t value. If your graph is not detailed enough, you can make this a little smaller, but it'll take a little longer to graph. And then initially, you might not know your x minimax and y minimax. So let's say we started with -5 to 5 on each of these, and then we can adjust it from there. And these are actually the position functions, not the velocity. So this actually will give us the graph of our two positions here. So there's robot A and there's robot B. So let's just change it. It looks like it's all in the fourth quadrant here. So now let's adjust this so we can focus on the fourth quadrant. The X minimum, we don't need to see the second or third quadrant, so I'll make that -1. X maximum, I'll leave that 5. Y minimum, let's make it a little lower. Let's say -7. Y max, we don't need to see the first quadrant, so I'll just make that 1 and regraph it. So there's robot A, there's robot B. So you can see there are, it looks like, a couple places where they do have the same position. The only thing we don't know for sure is, does that occur at the same time or not? So let's go ahead and enter these in the Inspire, and then I'll show you how to solve this with your graphing calculator. So for the Inspire, you go to New Document, Add Graphs, and then right now it's regular function mode. The way you switch it, you go Menu, Graph, Entry, Edit, and then instead of function, which is the default, go to the one that says Parametric, and then you can see you can enter them in. So our first one, again, we can put the fraction in there first if you want. It's easier to type in, is 2, and here you can just use the t right down here, to the t, and then divided by t plus 4. And y1, this will be our a, will be e to the t minus 4, and then hit the right arrow to get out exponent, -6. And here's your t min and max right here on the parametric one, puts it right here. So let's just change this to 0 to 6. The default is 0 to 2 pi. And there we go. And then for, oops, so let's change it back to, for this one, for both of them we'll make it 0 to 6. Okay, and then for x2, we'll enter in square root of t is the x-coordinate. And the y coordinate for the y position is, you can just put 0.5 t squared minus 3t minus 1. And then we'll graph this one too. All right, and now we can change the window side. Let's go Menu, Window, Zoom, Window Settings. Negative, let's see, let's make it the same as the other calculator. -1 to 5. X min and max, Y min and max. Let's make that -7 to 1. And we can see it right in there. All right, so now, as far as I know, in the parametric mode, your calculator can't solve these, so we've got to go back to regular function mode. So let's go back to the 84 and see how we go about that. So we want to see whether the x's are equal. So what we can do in our 84 is hit the mode button and go back to regular function mode. So we won't lose the stuff we put in parametric mode. It's just now when you go to regular function mode and hit y equals, it's back here. And you could just type these in like this, using x instead of t. But the faster way to do that, since we already have them in our calculator, for y1, I'm going to enter in vars, y variables, parametric, and I already have it in as x1. So I'll put x1, and all I have to do to change it is I just want to replace the t's with x. So you can just put parentheses x. And that's the same function I have here, just with 2 to the x over x plus 4. That's this side. And then for y2, I want xb, that was the square root of t, so I, again, can just go vars, y variables, parametric, and get x2, and then again, we just want to replace that t with x. And then window size, it's for the x min and max here, I want to make it 0 to 6, because we only want to look where they intersect there. And then go to second calc, number 2, 0. And it looks like I need to make my y max a little bigger so I can see where they intersect. Let's go to window here. I'll just make this 7. And go to second calc, number 5, intersect. So there's our x coordinate of our robot A for 6 seconds, and then there's the x coordinate for robot B. And you can see there's one place right here where they intersect, and then first curve enter, second curve enter, guess, enter. And we get 4. So these are equal when t equals 4. The x coordinates. But that doesn't necessarily mean they collide, because the y coordinates could be different. So, to see if the y coordinates are equal at that same time, go back to our calculator, go to y equals, and de-highlight these two. And now let's put in, well, let's write down what we're going to do on paper first. We're going to set y sub b of t equal to, sorry, let's do a first. Doesn't really matter which is which, but just to be consistent here. So y sub a of t equal to y sub b of t. So here's y sub a of t right here equals y sub b of t, which is right here. And again, let's use our graphing calculator to solve this. So now, de-highlight these equal signs, and now we'll put vars y variables parametric, and y1 of y1t, and then again just replace the t with x, so parentheses x, so plug x in to replace the t's. And then for y4, same thing, y variables parametric, and go y2, and then of x. Okay, and then we can just go second calc intersect, number 5. And again, we want to see at what time are the y coordinates the same. So there's the graph of the y coordinate of robot A, and then there it is for robot B. So you can see there is a place where they intersect there. So first curve enter, second curve enter, guess, enter. And notice we do get, it looks like it's not quite 4, but it actually is exactly 4. It's just your calculator's a little off there, and that's why on the AP test they just ask you to round it to the thousandths place. So sometimes beyond the thousandths place it can be a little off here. It is actually exactly 4. Another way you could figure that out is actually by substituting 4, since we know time 4, the x coordinates into these and see if they're equal. So if you substitute 4 in here, you get e to the 0 minus 6. E to the 0 is 1 minus 6 is negative 5. And you substitute 4 here. 4 squared is 16, times a half is 8, minus 3 times 4 is 12, so 16 minus 12 is, let's see, 8 minus 12, because I forgot to multiply by half is negative 4, minus 1 gives you negative 5. So they both kind of give you a y coordinate of negative 5 times 4. That's another way to confirm it's exactly 4 here. So there is a time 4 here. We're going to justify it, but let's see how we do this on the Inspire real quick. So on the Inspire, you would just go doc, insert, graphs, another graph one. And then here again, we can go var for the x coordinates, x1 of x. And then down, F2, var x2 of x. But let's change our window size, menu, window zoom. And again, we want to just look just between 0 and 6. And we can leave the y min and max like that. So you can see, then you go intersection again, menu, analyze, graph, intersection. Lower bound, click there. Upper bound, click there. And you can see it's right there at 4. And then you can go tab. You can uncheck these two. You can open up a new window too if you want. Or just uncheck these two. It's probably easier. And then for F3, go var. Type your F3 var y1 of x. Down, and then F4 var y2 of x. Enter, and just see where these intersect. So menu, analyze graph, intersection. Lower bound over here, upper bound right there, and you can see they also intersect right at 4. All right, so now all we have to do is write down our answer and justify it. So we can say the robots collide at t equals 4. And then to justify it, we can just kind of describe what we just figured out with our graphing calculator. Since, well, we kind of say this, except we want to say they're equal, not always equal to exponents, but specifically at time 4. So you can say since x sub a of 4 equals x sub b of 4, that means the x coordinates at time 4 equal, and y sub a of 4 equals y sub b of 4. That means at time 4 the y coordinates are equal. So that's how you can justify it. All right, then for part B, it says find the average speed of robot, and apologize there's a typo on there, I should say robot B, not robot A, from 0 to 6 seconds. So whenever you're doing the average, in this case on some interval, remember you start off with 1 over, in this case 6 minus 0, and then it's the integral from A to B here, from 0 to 6, of whatever you want the average of. In this case, it's speed, which remember for these parametric ones, the formula for speed is the square root of x sub 1, or the velocity of particle b to x coordinate squared plus the velocity of the y coordinate of robot b squared. So we don't have those yet, we have their position. So we can find those though. So I'll do that off to the side here. So this one we're done with here. So now if we find for robot B right here, x b prime of t. Well, this is just t to the 1/2. So when you take the derivative, t's to the power will be 1/2 t to the negative 1/2, which you can simplify to be 1 over 2 root t. So that's what we'll have here, squared 1 over 2 root t squared. That's the velocity of the x coordinate. Plus, now we need the velocity of the y coordinate of robot b. So y sub b prime of t. This one's a little easier. It would just be, bring down the 2 times 1/2 is just t minus 3. And then squared. Oh, and I apologize if one more typo I forgot. It doesn't actually work to calculate this from 0 to 6 seconds because you can see the velocity here is undefined of the x coordinate, and so that won't work. So one more change here, sorry about that, I forgot. Let's change this to the interval from 1 to 6 seconds. From t equals 1, so this will be 6 minus 1 instead of 6 minus 0. And then the integral from 1 to 6. There we go. And then dx here. Okay, so let's see how we calculate this on both calculators here. So with the 84, just go to second quit. And you can have it in either mode here. Whoops, I should have put a dt here. Probably easier to type it in if we have it in parametric mode, since we can just leave everything with T. So I'll switch to parametric mode before I type it in. So that way when I hit this button, it'll be T, not X. So, oops, hit the mode button here, and then highlight parametric again. And then second quit. And so we've got a 1/5 out in front. And then we want the integral, so math number 9, function integrate. And then what we want to integrate is the square root. And we've got this squared, so another open parentheses. 1 divided by 2 times the square root of t and then close parentheses squared, and then plus open parentheses t minus 3 close parentheses squared. And then we need a close parentheses to close off the square root. And then comma, t is our variable, comma, 1 is the lower limit, comma, 5 is the upper limit. See, I think I might have typed something in wrong here. Oh no. Yes, I did. It's 6 is the upper limit. Sorry about that. 1/5 out in front, so let me just fix this here. If you make a mistake, you can go second entry, and then just go back up here, and all I messed up was I accidentally typed in 5 as the upper limit when it's really 6. There we go. There we go. So there's our answer, 1.658. And here we actually have units for speed. Notice units for position or feet, units for time or seconds. So speed is the same units as velocity would be, it's just never negative. So it would be feet per second, would be the average speed of robot B. And let's look at how we do that with the Inspire. Just go dock, insert calculator, and then we put the fraction out front, 1/5, and then the integral from 1 to 6, and then we've got the square root, and then parentheses, 1/2 square root of x, and then that gets squared, plus, open parentheses, well, I guess if I want to be consistent, you can use x or t, it'll give you the same answer either way here, but just to be consistent, I will use t here. And then this will be t minus 3 squared. And then dt. I get the same answer. All right, let's look at part C now. It says on the axis provided below, sketch the graph of the path of robot B from 0 to 6 seconds. So we kind of already have what we need here. You can just go to the graph, go to, let's see, I think we're already in parametric mode. So if you want to just highlight robot B, you can de-highlight the equal to signs on x1 and y1 and just graph this one. See what it looks like there. So you can see that's what the position looks like there. Doesn't quite get to 3 over here. And it dips down, let's see, 1, 2, 3, 4, 5. It's like between 5 and 6 there. have to be perfect. We're just sketching it there. And then it says indicate the direction of robot B along its path. So notice you can see if you plug in 0, you get 0 for x, you get -1 for y, so it's starting right here as the starting point. And that means it's heading this way. So you can just put an arrow somewhere that shows it's going that way. All right, and same thing on the inspire. You can just look, go back here to our original graph here. You can see this is the graph of B right there. All right, and the last part of this one, a little bit different, says consider a rectangle with vertices at point 0, 0. So we've got a vertex right here, 0, 0, x sub b of t 0, x sub b of t, y sub b of t, and 0, y sub b of t. So where that's coming from is if you pick any point on here, let's say right here, this point, you could send it as x coordinates, x sub b of t, and then the y coordinate, y sub b of t, whatever that would be. And then to form a rectangle, notice you'd have a point here, and then that would have the same y coordinate as this one. So it would be 0, y sub b of t. That's where that one's coming from. And then you'd have another point right here somewhere, where it would have the same x coordinate as this point. So it would be still x sub b of t, but if it was around the axis again, you can see the y coordinate would be 0. So those 4 points here form the rectangle, one possible rectangle. And what we're trying to do is figure out from 0 to 6, so what time is the perimeter of the rectangle maximum? So first we need an equation for the perimeter of this rectangle. So notice if you were to draw it in here, you can see these two sides have the y coordinate giving you that, and these two sides are the x coordinate. The only thing you have to be careful is because it's in the 4th quadrant, your perimeter, it would be 2 times the x coordinate, so 2 times x sub b of t, and 2 times the y coordinate, y sub b of t. However, notice the y coordinates in the 4th quadrant are negative, and perimeter can't be negative. So you would have to multiply those by a -1, so rather than plus like we would normally have if we were in the 1st quadrant, it actually ends up being minus there. That way it changes these y coordinates back to being positive for perimeter. So, when you want the derivative, p sub prime of t, be 2 x sub b prime of t minus 2 y sub b prime of t. And normally you'd have to find these, except for the fact that we already did find them. Remember when we were doing part B to find the average speed. So this one was 1 over 2 root t. Minus 2, and then this one, remember, was y sub b prime of t. We already found it was t minus 3. So if we simplify that, and then we want to, since we're trying to maximize this, just like any other optimization problem, we actually set the derivative equal to 0. You can see this would be 1 over, the 2's cancel out there, root t, and then distribute the -2 minus 2t plus 6. So that, again, this one will be a little tough to solve without a calculator, because it's got the root on the bottom and then a t right there. So this is where we can use our calculator to solve this. So let's go to regular function mode to solve it. So go mode, oops, and change it back to regular function mode. Because as far as I know, it doesn't solve these in parametric mode. So y equals, oops, I guess I didn't change it after all. I thought I changed it to function. Oh yeah, I did, okay. So I don't think we need these in here anymore, but I'll leave them in there just in case and just de-highlight them. And then for y5, you would just enter in 1 divided by square root of, in this case it's going to be x there, and then minus 2x, and then plus 6. And again, we're just looking on the interval 0 to 6. So I think that was our window size already. So let me graph it. Yeah. Let's see, this gives us a graph of our derivative here. So if you draw your number line, this is the derivative of a perimeter. So looking at the y values, because it is the graph of the derivative already, from 0 to 6. Let's see, the y values start off being positive. So someplace a was 0, and then negative after that. And to find that exact value a, where that happens, because in this case this means the perimeter p of t would be increasing and then decreasing. We're looking for the maximum. So you can see it's got to be at time a. So using our calculator to find that on the 84. Second calc, 0. Left bound, something to the left of it, right bound to the right of it. Or if it takes a long time to do that, you can just type in, I know you can see the right bound would be 4, it's not. And then we'll guess somewhere in between those two, enter. And so we get 3.276 accurate to the boundless place. And normally if you had to actually find the perimeter, I would store this in the calculator. And then to find the perimeter, you would plug it into our original equation here before we took the derivative, just p for the perimeter. But here it's only asking for the time, so you don't have to do that. So you can just say the perimeter of the rectangle is a maximum at t equals a. The units for time again are seconds. And then to justify it would be since, well, you can justify, since that was the only possibility, it had to be here, you can justify it like you would a relative maximum, since p prime of t changes from positive to negative at t equals a. And then one more thing you should probably mention, just so you know, they know you thought about it. In this case, neither endpoint is a potential maximum, so you can say, and neither endpoint is a potential maximum. So then I know you thought about the endpoints, but realized, in this case, the endpoints are the potential minimums. All right, and let's see how we do that on the Inspire then. So for the Inspire, and you can just go to the regular function mode here, and then, whoops, hit tab to get back here. You can uncheck these F3 and F4, so you just see F5. And then again, we can enter in what we've got there is 1 over, put the fraction here if you want, 1 over square root of x. Again, to find the zeros, it has to be in regular function mode here. Minus 2x plus 6. And so you get the same graph there. And then menu, analyze graph, 0. Lower bound, click to the left of it, upper bound to the right of it, and you can see you get the same value there. All right, let's look at one more example problem. On this one, it says a laser is a device that produces a beam of light. The design shown above is etched onto a flat piece of metal using a moving laser. The position of the laser at time t seconds, so again our units for time are seconds here, is represented by x of t, y of t, and the xy plane. But this time we aren't given the position function. And it says x and y are both measured in centimeters, and t is measured in seconds. Again, the laser starts at position 0, 0, so it's starting right here, at time 0. And the design takes 3 seconds to complete. So the 3 seconds to complete, That's kind of telling you your T min and max. When you use your calculator, will be between 0 and 3. And here we're given the horizontal velocity, dx dt, and the vertical velocity, dy dt. And part A says determine the time, 0 to 3, notice, at which the laser is furthest to the right. So furthest to the right, you can see, looks like it's somewhere over here. And that's just another way of saying the maximum x-coordinate is what we're looking for. So in order to maximize the x-coordinate, we'd have to set its derivative equal to 0. But here, unlike the one we just did, we already have the root. So we're just going to set dx dt equal to 0. So let's go ahead and enter these in our calculator. So mode, I'm going to go back to parametric mode here to enter them both in together. Y equals, I'll clear these out. So we've got 2.9 cosine of t squared and 4.1 cosine of 2.5t. Okay. And then for the window size, now we're just looking 0 to 3. But keep in mind the graph here is not really, it's not the graph of what this looks like. That's why it doesn't match up with this. Because this is the graph of our velocity components, not the graph of position, which is what creates this, but we don't have the position equations here. So the graph isn't really helpful in this case. So then to solve this, you would just go to y equals, sorry, actually mode first, and then keep those in there, but switch it to regular function mode. And then go to y equals, and I'm going to clear these out here. Except for x sub 1 of t, of x, because that's what we want here. We want that equal to 0. And then change our window size here, 0 to 3, so we only see in that interval, and then second calc 0. So you can see the graph of the derivative there, dx dt. Let's see. Oh, I didn't highlight the equal sign, sorry about that. That's why I didn't graph it, so let's highlight that, enter. Now let's try to graph it. So you can see it starts off being positive, then negative, positive, and back to negative. So a little more complicated number line here, so let's draw that. dx dt from 0 to 3. Again, we're looking at the y values. So you can see it started off positive, then went to negative, positive, and then back to negative. So I'll call this A, B, let's see. That's where it was 0, 3 places there. And what this would tell us is the x-coordinate again is increasing, then decreasing, then increasing, then decreasing. So if we're looking for the furthest to the right, the maximum x-coordinate, in this case, notice there's two possible places. It could be at A or at C. So let's go ahead and find both of those using our calculator, using the zeros on there. We don't need to find B here, though, because that would be a potential minimum along with the endpoints. So to find A and C, let's go second calc, 0. Left bound, I'm just going to type in 1. I can see that's the left enter. Right bound, I'm going to type in 2. And yes, 1.5, somewhere in between there. To find A. So A is 1.253. And here we do need to store in our calculator because we need to compare these. So then I'll go second quits. Store alpha A. And now let's find C, so second calc. 0 again, number 2. And left bound this time, be careful, we got a lot of zeros, so it has to be beyond this 0. So it doesn't find this one, it doesn't find B. So left bound there, right bound, I'll just type in 3, because I know it's up to 3, and then guess, I'll guess 2.5, somewhere in between there. Okay, and we get 2.802 as our C value. And then we need to compare, let's store this in our calculator first. Second quit, store alpha C. We need to compare which one of these is actually the maximum. So let me go back to the inspire real quick, and then we'll do that. So for the inspire again, you can go to the regular function here, and go tab. Oops. And let's delete these out of here. Go control clear to get out of there. Clear, clear. The only one left in there is this one. For some reason F5 didn't clear out for me. Maybe you have to delete it there. Okay, there we go. I guess the clear doesn't work too well here. Let's try delete again instead. Okay. And then, oh, I don't think we've changed our functions, have we? Yeah, we have. Let's just start a new document. That'll be easier. New document, add graphs. Let's do the parametric right here. Graph entry edit, parametric. And enter in our two functions here for x1 and y1. So we've got 2.9 cosine of t squared, and y1 4.1 cosine of 2.5t. And then change this from 0 to 6.28, delete that, make it 0 to 3. There we go. So again, this isn't the graph of position, this is a graph of our two different velocities together. And then doc, insert another graph, and this one again we can just go var x1 of x. And then, oh, you can see there's way too many zeros here. We got to change our window size, menu, window zoom, window settings. Just go from 0 to 3 again. All right, so we get the same thing. We can find those the same way. Menu, analyze graph 0. Lower bound, upper bound. We'll store this one as A. And then menu, analyze graph, 0, lower bound, upper bound. We'll store this one as C. Alright, so now let's see how we can compare these two. So I'll write up here where we have a little more room here. So really, if we want to compare these, we want to know what the x-coordinate is of each of them, right? So we want to compare x of A with x of C and see which one actually is larger. So for x of A, these are really initial plus change problems, because we have the derivative dx dt, but the initial, notice, the initial x-coordinate's right here. 0, that's our initial x-coordinate. So 0 for both of them, plus the change. This one will be the integral from 0 to A, this one 0 to C, and we always, when the change is always the integral of the derivative, which in this case is dx dt. You can write the 2.9 cosine, or you can just write it dx dt either way. And and then times dt. T is our variable for those. And this is how you can kind of see it's going to give you the change in x. To see the dt's would cancel out and give you the change in the x coordinate, which is what we want. So here we're just trying to find the x coordinate of the laser's rightmost position and the time. So let's use, since we count them the same way, let's calculate one with the 84 and the other with the Inspire. So I'll do the A with the 84. So math number 9, integrate. We're integrating dx dt. So since I have an irregular function mode, that was my y1. Or you could put it in parametric mode and put in x1 of t. Comma, x here is the variable, and then comma 0 to a. And we get 2.835. We round it to the thousands place. And let's use, we do the same thing for C on the 84, but let's use the Inspire here. Oops. So doc, insert calculator, integral from 0 to C, and you can go var. You can either use y1 or f1 or x1 either way. I'll use the t1 here. dt. I'll use the other one to be dx. And we get 2.329. So in this case, the larger of the two is 2.835, so that's for the x coordinate, that's what it is, and the time. And it didn't say to justify, so you don't have to. You can say a laser is furthest to the right at t equals, since we just wrote down a there, we can say a. Just put the units for time here, seconds. When it's x coordinate, because that's for the x coordinate, is 2.835, and the units here, notice for the x and y, they're measured in centimeters. If you did have to justify it, all you'd have to say here is since x of a is greater than x of c. All right, and then the last part of this one. So what's the difference between the y coordinates? So difference in mathematics means you're subtracting them. Between the y coordinates of the laser's highest and lowest position from 0 to 3. So the highest is just the way to say the maximum, and the lowest the minimum. So here we have to find both the maximum and minimum y coordinate, and then subtract them to get the difference between the two. So in other words, we're trying to figure out, well, the highest point looks somewhere about right here, the lowest point is somewhere around here. We want to subtract those and see how far apart those actually are, the highest and lowest points. All right, so here we have to set dy dt equal to 0 to maximize the y coordinate. It's derivative. And so we can use our calculator to do that. So if I go back to the 84 here, we don't need this anymore, so I'm going to clear this one out and then put vars y variables, parametric, y1 of x, and then graph it. So you can see it starts out positive, then negative, and then back to positive. That's what I look at the y values. So we can draw our number line again. This time for dy dt from 0 to 3. And you can see it starts off being positive until some point A here where it's 0, then complicated than the last one. In this case, the y-coordinate would be increasing and decreasing and increasing. So let's say we start with a maximum. You can see the maximum would have to be an A or 3. So let's go ahead and find what A is. Second calc, 0. Left bound, 0. Right bound, 1. I can see it's somewhere between 0 and 1. And my guess, 0.5. So A is 0.628. And let's store it on our calculator. Store alpha A. So again, we want to compare the y-coordinates. So for the maximum, we want to compare y of A with y of 3. And again, you can see the initial right here. Since it starts at 0, 0, the initial y-coordinate is 0. Plus the change, here would be the integral 0 to A of dy dt. And here would be the integral from 0 to 3 of dy dt. Okay. So let's do the maximum with the 84, and then we'll do the minimum with the inspire, because overall it's the same process here. So we already found A on the 84. So integral from 0 to A and 0 to 3, we've got to compare those two, see which one is larger of the two. So math number 9, function integrate, and this one I had in as y1 here. So vars y variables y1, comma, since I have regular function was x, comma, the lower limit 0, comma, the upper limit alpha A. We get 1.64. And let's do the same thing for 3, and what you can do is just copy and paste here, or sorry, second entry, and then just go back here and change the A to a 3. And we get 1.538. So we're looking for the larger one. So there's our maximum value, 1.64. And then for the minimum, let's use the inspire for this one. Overall, it's the same process, except you can see for the minimum, the possible place of the minimum could be is either at 0 or at B. So we want y of 0, but that one we already know the initial is 0, so that one's just 0. And then we want to compare that to y of B, which we need to find. So let's use the inspire to find B, the other 0. Just going to open up a new document, it'll be a little easier here. So add graphs. Menu, entry edit, parametric. So x was 2.9. Cosine of t squared. And y1 is 4.1. Cosine of 2.5t. And again, just change this here. We're just looking from 0 to 3 seconds. And then doc, insert another graph where we can just use y1 of x. But again, we don't want all these zeros. We want to change our window size, just 0 to 3. So we'll only look on that time interval. So you get the same graph, but now we want to find b for the minimum. So menu, analyze graph, 0. Lower bound there, upper bound there, and there it is. So B is 1.885. And we store that in our calculator. Highlight it, var, store as B. And now we need to set up our include. This one would be initial 0, integral from 0 to B of dy dt. And then we can see what this one's equal to. Based on the graph, you can kind of tell this is definitely going to be lower than 0, because you can see this is a negative y coordinate down here. So we should expect to get a negative answer here. So doc, insert calculator, integral from 0 to B. You can either use y1, f1 we have it in there, or y1 either way. If you use y1, it would be y1 of t dt. If you use f1, it would be f1 of x dx. And we get negative 1.64. So we're looking for the lower of the two. In this case, this one is our minimum. And then finally, it says what's the difference between them. So to get the difference between them, you would just take our maximum minus the minimum to see how far apart they are. And you can see that would give you 3.28. And the units here are centimeters. And that concludes the notes for AP Calculus on the topic of parametric functions with the graphing calculator. Continue.